Someone took the legendary Bad Apple video and compressed it into a neural network that weighs less than 3 megabytes. Someone took the legendary Bad Apple music video and compressed it into a neural network that weighs less than 3 megabytes. The original Bad Apple is a black and white animation that has become a staple of tech demos for decades. But this time, instead of encoding it as pixels in a video file, the creator trained a small neural network to memorize the entire thing. The result is a model that can regenerate the video from nothing but learned weights, all stored in a file that barely registers on the size scale of modern video files. So how does this actually work? The network is a 5-layer multi-layer perceptron using something called Siren, which stands for sign activations. It takes a 3-dimensional coordinate as input, the frame index, the vertical pixel position, and the horizontal pixel position. For each coordinate, it outputs a single grayscale value between 0 and 1. The video is stored implicitly in the network weights themselves. The model uses 5 linear layers with 512 hidden units each, with a frequency parameter set to 30 and a sigmoid output layer. To play the video back, you simply evaluate the network over the full grid of coordinates. The source video is the full Bad Apple animation, with 6,524 frames at a resolution of 854 by 480 pixels. That is roughly 2.7 billion pixels total. The creator subsampled this to 1,620 frames at 384 by 384 pixels, which is about 1/10 of the original pixel count. That represents a 2.8 times spatial reduction and a 4 times temporal reduction. The subsampled video itself is only 700 kilobytes, while the neural network that reconstructs it is about 3 megabytes for the Float 32 version and 1.6 megabytes for Float 16. At first, the creator tried a ReLU-based multi-layer perceptron with low-frequency Fourier features, but it plateaued around an MSE of 0.12. The breakthrough came from switching to Siren, whose sign activations naturally add higher frequency content without needing positional encoding. But that early model had a problem. It could only shift information slowly, so quick motion came out blurry. To fix this, 2 key changes were made. First, time stretching. The time coordinate was scaled by 4 times relative to the space before the first layer, giving the network 4 times more temporal capacity. Second, motion focus sampling. Since Bad Apple is about 90% static black, uniform pixel sampling starved the moving edges of gradient. The fix was to draw half of each training batch from pixels that changed between neighboring frames. The improvements were dramatic. Validation MSE dropped from 0.0795 to 0.009, which is about 9 times better. Compared to the old model, high motion frames were 3.6 times closer to ground truth, and static frames were almost 15 times closer. Out of 398 sampled frames, 398 out of 400 improved. The training pipeline used a single shared network on the whole volume with no per-frame latence, a cosine scheduled atom optimizer with weight exponential moving average, followed by a low learning rate polish pass over the entire video. The 12.6 megabyte checkpoint includes the weights plus atom moments plus the EMA copy, but the network itself is only 3.2 megabytes. Some viewers were confused about the compression aspect. The subsampled video is 700 kilobytes and the network that reconstructs it is about 3 megabytes, so technically the network is larger than the source. The creator noted in the post that it has not been compressed very much, but the goal was seeing if they could in learning rather than achieving super compression. There is also a full resolution model being trained on the non-subsampled video. The playback runs at about 8 frames per second for a duration near the original 3 minutes and 37 seconds, or at 12 frames per second, it runs at approximately 1.6 times fast forward. The community response brought up some great technical points. One commenter asked about using deconvolution and positional encoding instead. Another explained that Siren replaces the activation with sine waves, so you do not need positional encoding to capture high-frequency details. Someone generated a between frames video at 60 frames per second showing interpolated motion. There were questions about why subsampling was used first, with the answer being that training on the full video would take too long. One commenter pointed out that for a nearly black and white video, you could encode it at 1 bit per pixel and beat the network size easily, suggesting this is more of a fun experiment than a practical compression method. Others asked about perceptual loss functions like wavelet or Fourier domain MSE. What makes this project interesting is not that it beats traditional video codecs, which have decades of optimization behind them, but that it explores a fundamentally different way of representing video. Instead of storing frames and compression metadata, the entire video is encoded as a continuous function that the network has learned. It is a proof of concept that neural networks can memorize and regenerate visual content from implicit coordinate mappings. The creator is now training on the full unsampled video and has mentioned trying upscaling resolution by passing fractional inputs to see if the model generalizes. One commenter summed it up nicely, saying it is like watching the original through very old glass, wobbly with imperfections, but the point is appreciating the experiment itself rather than treating it as a solution space optimization. The full resolution videos, checkpoints, and code are all available on the creator GitHub page. If you enjoyed this deep dive into neural video representation, hit subscribe for more explorations at the intersection of machine learning and creative computing. Check the description for the GitHub link and let me know what you think in the comments.